Hello and welcome to this video on the basics of the Solow Growth Model and the basic setup of it. So the target audience for this video is a student either in a high-level Intro to Macro course or for most an intermediate-level macroeconomics course. So I'm TAing a macro course now, and there's a lot of good text floating around the internet on the Solow model, but not too many videos and not as many examples and applications of problems as I'd like to see available to students. So with this series, I hope to give a pretty comprehensive review of the trickier material that you'll be expected to know about the model, and that is in a typical undergrad macro course on macroeconomics. Also, in terms of how I like to approach all the material, I prefer to focus on the nitty-gritty details and examples and problems that you'll likely be asked on an exam. So I'll cover the more boring and technical material related to the model, rather than the funner, more intuition that you'll hopefully get from a professor and lecturer. So the technical stuff is important for your grade and doing well in any typical macro course. I hope. This video is also one of many others. So if you want to skip ahead to a specific topic or to the other topics, check out the video description for useful links on Solow. So the Solow model, aka the neoclassical growth model, also known as the Solow Swan model, also known as the exogenous growth model. It's a model to help us understand why economies might grow, and at the very least, it's part of the story. So the Solow model is usually the second model of economic growth taught to students. Solow usually comes right after your professor points out that a macroeconomy can grow if you increase the factors in the production function. So if you increase the quantity of capital or you increase the quantity of labor, that's going to increase overall output, and the economy's grown. At least it's grown, in a form of growth. The classical growth model, so where the Solow model is a neoclassical model, in classical growth theory, in my mind, classical growth theory basically boils down to pointing out that the economy benefits from increased specialization. So specialization within an economy and trade between economies allows for economies of scale and overall benefits. So kind of think comparative advantage when you think of classical growth theory. The Solow model is kind of the next step. The Solow model, it's a simple model of just how an economy works. So you got capital, you've got workers, you've got a goods market, and you got more. And it presents a simple framework on how these things can come together to result in sustained economic growth in a way that rings, true intuitively and somewhat empirically as well. At its very most basic, to summarize it as simple as I possibly can, so probably not too useful, but its most basic, the Solow model shows that in the long run, an economy's rate of savings determines the size of the capital stock and therefore the level of production and its per capita output. So, the higher the rate of savings, the higher the stock of capital, and the higher the level of output. The model relates economic growth to changes in factors, so that's like labor and capital, and to preferences to save, that's the savings rate, plus other features of the economy like the depreciation rate, population growth, and technology. So we'll get to all those details right now. So the first part of the model I should point out is this introduction of the concept of time, where a lot of models you learn are kind of static models. There's maybe one period or another period. There's this, and it relates to that. The Solow model is a dynamic model, so there are economic variables that evolve through time. Thus the model is in discrete time. It could also be worked out in continuous time, but that's continuous time for later. So time is broken into periods. You have one period, and then the next period, and the next period, and it's all marked with these little subscripts, some t. So take a variable, like y sub t. This means that it's the value of all output in the economy at time t. If you were to have a subscript, so y sub t plus 1, that would be the value of y, aggregate output in the economy at the period t plus 1. And it's the same, for capital and other variables that have a time subscript. So it's pretty intuitive use of time. The next thing to note is that it's a closed economy, so there's no trade in this model yet. In fact, we usually don't even bring trade or exports or anything like that into the model at all. There's also one good in the economy. We're going to call it Y, or output, or income. Again, this model is a super simple model. You can maybe think of Y as something like value, or the value of all goods and services produced, but technically there's just one good in the model, so there's one amount of production, one amount of income, and that income could either be used for investment or consumption, which we'll get to in a second. There's kind of the following 5 key variables of the economy, and by variable I mean that they're dynamic, they either change through time, or they're endogenous, they're determined within the model. It's sometimes more complicated than that. So, for example, labor, for the simple version that I'm going to cover, is fixed in this model, so it's treated as exogenous. But later on, we'll introduce a population growth rate. And then we're also going to have a number of parameters. So the first parameter. Well, first of all, parameters are just kind of treated as exogenous and constant. There's no real endogenous or internal way that the savings rate or depreciation rate or the other parameters later introduced. There's no endogenous way that those things are determined. They're just given to you. So the savings rate is blah, the depreciation rate is etc. We also have the savings rate, that's S, so notationally designated by the lowercase s. This is a percentage, so it's a number between 0 and 1 of one's income that is quote-unquote saved or investment. The rest of the income is consumed. So over here in the goods market, right, you have a certain amount of income. That's how much is produced in the economy. That income goes to people, and people could do 2 things with it. They could either consume it, which is our proxy for welfare, or they could invest it. And another way to rewrite investment is it's a certain percentage, the savings rate, times overall income. And then consumption is just 1 minus that savings rate, so that's the consumption rate. That's the portion of income that's consumed. A little bit more on investment, that's the portion of income that's saved. So what does that mean that we're saving it, right? Consumption is something that's pretty clear. You imagine people use it, it goes away, it disappears. But what happens when we save something? Well, savings is invested into the capital stock. That is to say, it's converted into capital, it's added to capital. So I, right here, if there's anything that's saved, it adds to the capital stock. L is the labor supply, so that's kind of the size of the labor force or the population, or the aggregate number of households, depending on how you want to think about it, all at time t. Notationally, I've seen in other textbooks, I think Blanchard and maybe others refer to it as N, so N sub t for labor or population. And then in terms of technology or production, right, so we have a production function down here. It takes in the factors, so capital and labor, and you put those things together into the economy and you produce a certain amount of output. And then the functional form that we're going to be using, and in fact all intermediate textbooks that I've seen so far, the major ones anyway, use a Cobb-Douglas production function or a form of the Cobb-Douglas production function that looks something like this. So you add capital, you add labor, that increases output. And they're doing construction outside my window, so I'm going to pause this video for a little while. Okay. Sorry about that. Outside my window, there's an open pit with construction workers periodically jackhammering and cutting something or another. So I chose poorly as to the day to make this video. Anyway, next, let's now turn all these variables into per capita values. So notationally, first off, when I say per capita, note that I'm saying per capita, not per capital. Per capita as in per worker. Notationally, the lowercase for each of these things, lowercase k, lowercase y, lowercase I, and lowercase c, corresponds to per capita values of each. So there's an aggregate value, and you divide that by the labor force. So per capita capital is aggregate capital divided by the labor force. Per capita output is aggregate output or income divided by the labor force. Per capita investment is aggregate total investment divided by the workforce population. And then per capita consumption is total consumption divided by the workforce. I should also say a few more things about production technology. So let me set that up for you. So we need to state a few assumptions to fully characterize the production function. These assumptions are required for the rest of the model to work and end up with the results that we end up with. If we relax these assumptions too much, we might lose or not fully get all the results we end up with. I sometimes feel a little weird about going over or mentioning these assumptions to an intermediate level econ students, since we generally gloss over that in an initial class. But these assumptions are required to create the proofs of the interesting, results and conclusions. So for completeness, I thought I'd kind of quickly go over them for you. So first off, we need our production function to exhibit constant returns to scale. Constant returns to scale implies that, if we double the factors, like we double capital and labor, then we double the output. It's going to be required because when we convert our production function into per capita terms, it gets this nice result where per capita consumption is just a function of per capita capital. We also need to kind of characterize the shape of our production function. So we assume that per worker production function is characterized by positive and diminishing returns to scale. So by positive returns to scale, this means that if we increase capital or we increase labor, then we're going to increase production, right? So we have a certain amount of output, we increase capital, we can increase labor. No matter what, it's always going to go up. So output's always going to go up if we increase either or both of those factors. But by diminishing returns to scale, it implies that so as you increase capital, output's going up, but it's going up at a decreasing rate. So this is a 3D image of a Cobb-Douglas production function. So diminishing marginal returns implies that along this axis right here, we're increasing labor. The vertical axis here is production, Y. So you can see as we increase output, production's always going up, that's that positive, but it's going up at a decreasing rate. So the shape is concave, like a cave. Okay. So next up we have these not assumptions. It tells you that, if capital or labor is 0, then the return to adding a little bit of capital or adding a little bit of labor is infinite, right? So I guess if capital or labor is at 0, then the production function is at 0, right? So if this K is 0 or this L is 0, then aggregate production 0. So adding an infinitely small amount of extra labor, starting off at 0, adding a tiny bit, that's going to mean the production's positive, implying that the return to that bit of capital or the return to that bit of labor, if we start off with 0, is infinite. And then also, if our capital stock is infinity, then the value of adding a little bit extra capital is 0. And then similarly, if we have an infinite number of workers, adding an extra worker doesn't change, the level of production at all. So that kind of characterizes the shape of that production function. So the slope of this point over here, right at 0, is infinite, and the slope as we increase labor to infinity is 0. And then the last two assumptions are just kind of tell you that the factors are important, right? So the first one here is if there's no capital, if there's no labor, there's no production. The next one, if there's no capital, but there's some labor, once again, no production. And then the same thing, if there's a little bit of capital or there's some capital but no labor, production again is 0. So basically the factors are important. And then lastly, the cross-factor elasticity, can't remember what this is exactly called, but it tells you that capital and labor are complements. That's the cross-partial. So the cross-partial derivative of the production function is positive, implying that capital and labor, the factors, are complements. So lastly, let's talk about the capital accumulation equation. Well, lastly in the setup. The capital accumulation equation, you might also see it referred to as the law of motion of capital. It tells you how capital changes through time. Before, the model with just the production that preceded discussion of the Solow model, the capital stock K was just taken as exogenous. So the Solow model makes the stock of capital endogenous. So it makes this little process that defines what capital is going to be from one period to the next. So the stock of capital next period, so K sub T plus 1, is equal to yesterday's stock, right? So you had some stock that you started off with, and next period is going to be based off that, minus depreciation, where depreciation is the rate at which capital is destroyed from one period to the next. So you could think of it, if capital lasts, let's say, for 100 years, then the depreciation rate is about 1%. So it's some rate that defines how capital kind of like degrades over time. And then plus investment. Remember, investment is the portion of one's income that people save, and that savings gets converted into capital. So you take the current capital stock minus how much depreciated plus investment, and that's going to give you the capital the next period, the capital stock the next period. Cool. So that's the setup of the model. Before we get to the steady state, let's Let's think about how all of these things kind of add together. When we get all of these things together in motion, this is a dynamic equation, and we've kind of defined how things can change from one period to the next. What happens? So let's kind of work through the model and solve the model. So as our first step, let's convert all our stuff into per capita terms. So we're going to take the production function right here. We're going to find what it's equal to in terms of per capita. So first off, as a notational kind of trick, think about per capita production, right? So per capita production, lowercase y, is aggregate production divided by the quantity of labor, so capital Y divided by capital L. Another way to rewrite that, right, is it's just the production function. Y, the production function, is just the production function, so it's a function of capital and labor divided by L. And then since this production function is constant returns to scale, we know that if you multiply something by since the production function is constant returns to scale, if we multiply the factors in the production function by some amount, then you'll increase output y by that amount. So similarly, it works the other way. If you reduce aggregate output by some amount, then you can do that by reducing the factors by the same amount. Thus, lowercase y, per capita output, is equivalent to the production function with per capita factors. So note that this only works because of constant returns to scale assumption. Now, the capital stock is divided by the labor force is per capita. So, the capital stock here divided by L, that's just lowercase k, that's per capita capital. And then the labor force divided by labor force, that's just 1. So as a notational kind of thing, we denote output per worker, output per capita, as f of lowercase k. And then to drive the point home, we have a nice squiggly f there. Cool, but remember our production function, right, was this Cobb-Douglas production function, so where A is total factor of productivity, K is capital, L is labor, and then we have this alpha here standing in for capital share of income, so parameter. Let's apply that to our per capita production function. So here's y as output is equal to that. That's just notationally. Here's what it is definitionally. So we're using Cobb-Douglas production function, which all the major intermediate macro textbooks uses in one form or another. So we divide that by L to get it in per capita terms. The next two steps are just kind of like algebraic, just simple algebra, and it all reduces down to the following. So output per worker, y, or notationally f of k, you'll see, is equal to total factor productivity times per capita capital raised to alpha, where alpha is the capital share of income. A lot of times in textbooks, they'll just assume that total factor productivity is 1, and then a lot of times in textbooks, they'll give you a value for alpha, so they'll make it like 1/2 or something like that. But, I want to keep these things pretty general, so I'm going to stick to this. But you can imagine, when you look at a textbook, they'll give you a production function, and they'll maybe make that a 1, which makes it go away, and so forth. Cool, so now we got our production function right here in terms of per capita terms. Cool, so the plan of action now going forward is we're going to try to find the steady state level of capital. So in order to show the steady state level of capital, we're going to need to show, we're going to work with the capital accumulation equation. And a steady state level of capital is a level of capital such that the idea is that k sub t plus 1 equals k sub t, right? So a steady state level of capital is one where capital is the same through time. So we're going to need to tweak this a little bit, first off to convert into per capita terms, and second off to deal with the actual production function we're working with to be able to solve for that steady state level of capital. So that's our end goal, is find the steady state level of capital, and all that we're doing now are steps to get to that goal. So just reminding, here's the capital accumulation equation, right, which was pretty straightforward, we worked with. Rewriting things a little bit, capital next period, the capital stock next period is equal to the existing capital stock less depreciation plus any investment. We know what investment is, right? Investment is just the savings rate times output. So up next, we want to convert things in terms of per capita terms. So what we're going to do is divide this equation right here, divide both sides by something that's the same thing, right? So the labor force is assumed to be constant, right? doesn't change through time in this version yet. So k sub t plus 1 divided by L sub t plus 1. Basically, we could both divide